and now we're going to do loop invariants. And the first examples are really, I was finding, people were failing the test, so we would get down to what are they missing, and it's simpler and simpler examples keep getting shoved at the beginning. So the first examples are definitely easier than will be on the test, but it'll get us warmed up a little bit. All right, so what are we doing here? We have one basic loop, and there's some data structure that's going to change every iteration, and each iteration we take some step towards our destination, right? All right. Oh, here we go. Right. So I think I sort of emphasized last class that whether you're doing iterative algorithms or you're doing recursion or anything, a computation can kind of be scary and complicated, right? And the way to deal with that is to take each step at a time so that you understand a single step, and then it's about having some belief that then the whole of the pieces get put together, right? So in some ways, whatever your belief system in life is, you want to kind of work it out so that every day you're not rethinking it, right? So this is going to be another belief system that you need to work out and what we're working out here is that if you put all these pieces together, in the end you get an algorithm that works, right? So every time you don't have to rethink that. So here's just it's like a baton race. You know those races where somebody gives you the baton and your task is only to run around once and hand it to the next person, right? And in fact, the analogy comes on further because the first person brings the baton, right, establishes the loop invariant, and then we have one person for each time around to maintain that loop invariant, and then we have one person at the end to run across the finish line. Let's see, are we moving? Are we moving? Here we go. I hit it a couple times and it goes too far. So what is a loop invariant? It's not an action, all right? So put that in your brain right now. If I ever say, what is the loop invariant for such and such, and you give me an action, then you will get 0, right? Because a loop invariant is not an action, right? It's not the step you take when you go around. It's a yes-no picture at the top of the loop telling you what's true at the top of the loop, right? It's specific enough so we're kind of grounded where we are, and it's broad enough so that it can encompass all your iterations and everywhere you might possibly want to be, right?
So, Professor, would a loop invariant kind of be like a Boolean condition?
Yes. Was there more to that question?
No, that's it.
Excellent. Sorry, I interrupted you pretty fast, so I didn't want to seem like I was being too abrupt on you. All right? And again, you've seen in this picture already different ways of looking at something, whether the black or the green. We saw that. Everybody should study up on Escher. So the ways you guys are taught how to do computer science is code. And what is code? It's a sequence of actions, right? So if I'm telling you how to get somewhere, I could say, go straight for so far, and then turn right, and then go straight for so far, right? And, that's perfectly good. But, if you're me, I can only remember the first step, and then I get lost, right? So what another alternative is to give landmarks, right? I could say, well, I was born in Washington, then I went to Waterloo, then I went to Toronto, then I went to Berkeley, then I ended up at York, right? These are landmarks kind of in my life, right? And one of my funny thing that happened to me once was my aunt was giving me landmarks to get to her house. And the landmarks were, go forward till you get to a McDonald's. Well, I was in the wrong state, but, you know, you go forwards enough in America, you get to a McDonald's, and then you turn right. And so that wasn't as useful. But anyway, our goal here is to almost throw this away and focus on this, you know? You're going to tell me where the places you're going to be along the computation, and not so worry as much about how do you get from one to the other. Right? The idea is that if these landmarks are close enough together, then anybody could write the code to get from one landmark to the other. Right? What actions? Right? So I guess the way we're thinking about it is you write the sequence of locations, and then, you know, I remember I talked about standing on a subway talking to your friend. So you might start, you don't even need to do the locations, the landmarks in order, right? You can leap in the middle and say, well, if you're going to my house to York, at some point you might want to be at the St. George station, right? And then the guy you're talking to could sort of say, well, how do you get to St. George station? Well, at some point you want to be at the Ossington station, right? Okay, well, how did you, right? And any jump where your friend is good with, he's just, you know, she's not going to ask you about, right? And so that's kind of what we're doing. All right, so here's some code, right? And I don't like reading other people's code, right? But you can sort of try to figure out what this code's doing. It's doing a bunch of maxes, and then in terms of landmarks, right, we can say here's a landmark that we have at the precondition is going to say, hey, we have some input, right? And then the postcondition, we're going to say, hey, we found the maximum, right? And then we can think of other landmarks, right? We can have a landmark that we say that of this list, 4 is the maximum, and of this list, 5 is the maximum, right? These are various landmarks, right? And so, right, so if I tell you what these landmarks are, and then you can think, well, that's great, right? So each of these, right, are pictures or assumptions, right? You can say this, what is this landmark? This landmark is saying, if you consider the first 3 numbers of the input, right? I didn't make this, you know, picture. You have to do some sort of assuming. You know, you could formalize this, but you know, you can probably pretty guess that from this picture we're saying we have some input, and what is our picture is that if you look at the first 3 numbers, we know the maximum, right? You can write that down formally, or you could try to draw some picture which helps you with that. Right, so now, right, we can see how do we get from this to this, right? And I guess I haven't even told you what m is. I'm going to assume that m is this number here, right? So how do we get from this line to this line?
We take another number from the list.
Yeah, we take another number, and that's going to be, in this case, the 7. And now what do we do with that next number? Exactly. Excellent, right? Here, we know that 5, here we're not diving back into the entire computation, are we? We're not going back to say how we got there. Remember I said we fly in from Mars? We're using the fact that this is true and not worrying about how we got it. We're just going on faith. So we know that the 5 is the maximum of those things, and we want to figure out what's the maximum of those things. So really, we only have to compare these things, right? So that's the same. You'll note that part's the same. And so what do we have to compare? The max of M, which is the max of the purple, and the max of the 7, which is our new number. Right? Everybody following this? And you see this is really easy, but you know on the test half of you are going to bomb it, so pay attention. Right? And so here are the landmarks, and here's the code in between. Right? So remember, if you're thinking about our Escher picture, we can focus on the sequence of landmarks, or we could focus on the sequence of actions. Right? And there are two different ways of looking at it, and hopefully you could go back and forth between the two. Right? My feeling is that landmarks, unless they tell you a landmark at McDonald's, the landmark is helpful, is more helpful than go straight for 20 meters, right? So, all right, so this is kind of a repeat of what we're saying, right? Right, so these assumptions are particular types of assumptions, right? An assumption about what's true about the input is called a precondition. You probably all know that already, right? So what's our picture here? We're saying, well, the input is an array of values. What do we know? That tells us something, right? It's not a donkey. It's an array of real numbers, maybe, right? The postcondition is the assumption, that the statement that's true when the program returns, right? And it's somewhat linked to the precondition, right? It's talking about, in this case, what's our postcondition? Somewhere we're going to get it, right? Postcondition is of the input that we have, M is the maximum, right? And you might note here, I use two slightly different notations, which you should be able to move between. Again, this is different ways of looking at it, right? This way is looking at it as this is an array filled with numbers, and this is a set of numbers, which the numbers in the set are the numbers in the array, so that we can talk about M is the maximum of a set, right? Then what is the loop invariant? The loop invariant is what's the assumption that needs to be true every time you're at the top. And in this case, we could have a loop invariant that says, if you look at the set of first I numbers, and I wouldn't have cared if you had said A1 to I, right? We just might want to make sure that we're all on the same page. M is the maximum, right? So, in fact, there are two numbers here. It's telling us that we have these two new numbers, I and M, right? And so that's our data structure that we're changing as we go through. We're going to be changing I and we're going to be changing M. And it tells you a relationship between them, right? With respect to the input, which in this case it's never going to change, right? It's telling us we have some I, and what is M? M is the maximum of the first I guys. Right? Everybody go to that? That's kind of the nature of what we're going to be doing here. And so what are our steps? The first step is how do we establish the loop invariant, right? We want to do the easiest possible code to establish the loop invariant. And here, so I like drawing pictures, right? Or write down or draw a picture of the loop invariant, right? Sorry, of the precondition. Then draw a picture of the first iteration of the loop invariant. Yeah?
Can loop invariants still be things that might be untrue as long as you're breaking out of the loop? Like the loop condition itself is not a loop is it, or is it not a loop invariant?
No, you don't want your exit condition to be in there, okay, yeah, because we're going to get to the post condition, yeah, and there we're going to use the loop invariant still true.
Okay.
We want the loop invariant to be true when you drop out too.
So the loop condition is not a loop invariant.
The exit condition, no,
yeah,
no,
okay,
no. In fact, yeah, I mean, we're going to have some whole discussions about how people often will do things wrong with that.
I'll
Yeah. All right, so here I'm drawing a picture of what I want the loop invariant to look like the first time. And, then we can write code to get from here to here, right? Where's our code? There's our code. Really, i's 1. Now, of course, here I have these slides from a million years ago. In fact, I probably said, is it Java or is it C or is it pseudocode? We don't really care, right? So, and this is kind of where you have to, when you write code, people's code is often off by 1, right? And that's somewhere where having these loop invariants really helps you pin down what exactly do I want to be true here and make sure that I'm not off by 1, right? So here, you can see, well, if this is my picture, and then it's saying that, right, what's I? Well, do I want I? I has to specify the subregion, right? So now is I indexing the last guy, or is I indexing one further, or I indexing one before? You got to think about how you're implementing that. And then you have to think, well, if I is indexing this way, right, does my array index from 0, does it index from 1? Right, you got to think about all of those things. And right in here, sometimes I index my arrays from 0, and sometimes I'm 1, depending on my mood of the day, right? So here I'm doing it from 1, and now what do I set in to be? It's to be the first one, all right? Now, I don't know if I'm going to have this in this next moment of the slide, but often when I establish a loop invariant, I want to do it even easier than this, right? If you roll this loop invariant back 1, then actually the one advantage of I equaling 1 is because m is the maximum of one thing, right? So that helps us kind of think about that. So if we rolled back 1 step and I was 0, right? I really like empty sets and empty trees and empty, right? Because if you do it in recursion and it's the beginning. Right? And so many people I find who are coding are afraid of the empty set or afraid of the empty tree. Right? So I wouldn't be. If you roll this back and we want to set I equal to 0, right? Then you would have to think, now m is the maximum of the empty set. Right? And you have to think, what is the maximum of the empty set? Is it, well, any ideas of what the maximum of the empty set is? Well, I would go negative infinity, right? Now you might say, why negative infinity? Well, because when you take your next number, you want that to be the maximum, right? Remember, our code is going to take the maximum of our previous m and the new one. And if your previous one is negative infinity, then you're good to go no matter what, right? So that's one place where you can think about, right? So, here I said it, all right? It's good to know that I'm consistent one year to the next, right? Why is it, right? It's negative infinity is bigger than every element in the empty set, right? In fact, you could say, what's the definition of maximum? It's the smallest number that's bigger than everybody in the set. Right? Here, negative infinity, you got to admit, is the smallest number possible that's bigger than everybody in the set. Right? I just thought of that right now. That's pretty good. I should put it here. Smallest number bigger than everybody in the set. All right, so that's what we got here. So, less good. All right, so, yeah, I don't even know why I'm saying that. It's less good. We're all in agreement. All right, so here we got our initial code. Here, right, we're building out our code, right? We have a loop. We have the statement of the loop invariant. We're filling in the code here to establish the loop, right? We're going to have to write this code, and we're going to have to write this code. All right? All right, so how do we maintain the loop invariant? Well, we have to think about how to get from here to here. And so my recommendation is you think about a generic one, right? Again, right, we're flying in from Mars. we got a generic here. We got a generic I, we got some M, and we know this is true, right? And then we have to write the code to make, there's two things we have to do, right? Everybody know the two things? We need to make progress, and we need to maintain the loop invariant, right? I mean, one way of maintaining the loop invariant is to do nothing, right? But that's not very useful, right? Or we could try to do some actions, but if it throws us into the left field, then that's no good, right? We have to come back on the path and maintain our loop invariant. All right, so here's the code that we came up with before. Well, right, so the advantage of a nice clean loop invariant is it tells you what's true now, so it helps you not being off by one, right? It tells you that we have the maximum up to the I place, and so who do we have to look at next? Well, clearly we got to look at the I plus first next, right? So that's why we're comparing I to the M to the I plus first guy. And then the progress, where are we making progress? Well, clearly what's our measure of progress is the number of numbers that we've looked at, and that's I, and so we need to make I1 bigger. Right? Everybody good with that? Postcondition. Now we got to get the postcondition. Now there's two things to get the postcondition. The one thing is at some point you have to exit the loop. Right? So we will have to deal with that, and we'll deal with that by having a measure of progress that starts somewhere reasonable and you exit when you get somewhere reasonable. But in this case, it's pretty straightforward. We don't even have an exit condition yet, right? But so right now we're going to just pretend that we will exit at some point, right? And we're going to prove that the program works, assuming that you exit at some point. And when you exit the loop, there are two things that you know. What do you know when you exit the loop? Yes, you know the loop invariant is true. Why? Because you maintained it. What's the other thing we know? You've made a bunch of progress, but how can we narrow it down to something really, a condition that you know?
The exit condition is true?
Exactly. You know the exit condition is true. Why? Because you exited, right? Right. So exactly. So here right, then we got the maximum of the whole array, and we need to output 7, right? So we need an exit condition. Here the exit condition is in, because the loop invariant, again, this is where you get the one-off errors. You have to say, well, the loop invariant tells me that I have the maximum up to the guy indexed by I, which is also in my notation the number of numbers. And what's in? How many numbers do we have? We have n numbers. So when I equals n, the loop invariant tells us that we're done, right? So we have an exit condition, and then we return it, right? So here, maybe we have it on. Let's push the button and see what we have. Nope, we didn't have it, right? See, what we're going to be building up to is saying, if you know the loop invariant's true, and you know the exit condition's true, and you do this little code here, then you get the postcondition, right? And this is pretty straightforward here, right? If I is n, and we know the maximum of the first I, then we know the maximum of the first n, which is exactly what we want here, but, right? But I guess the slight difference is, maybe I should have said the postcondition is that this maximum is returned, right? Because once you return, we don't have a value m really anymore, right? So I should say m is returned. This is returned, and so then the action you have to do is to return m. Right? Everybody following this? Yeah.
In your loop invariant, the m is like the previous iteration's maximum, right?
Well, I get a little nervous about previous. It depends on you're at the moment before this iteration and this iteration. So, so in a sense, it's their maximum, or it's the maximum of, let's state it the way it is. It's the maximum up to I.
And I, in this case, like, because if you continue down in the code,
Right.
into your algorithm, you
Right.
got a to I plus 1.
Right.
So you're at this point.
Yeah.
Everything prior to this,
Yeah.
m is the maximum.
Yeah.
Now when you compare it to the next element, that's where you check for m, right?
Yeah. Yeah. The reason I'm a little nervous about it is you're talking about what happened in the past versus what's happening in the future, and you have to keep track of what do you mean by, right? So here, I just want to say this is a static picture without time.
Right.
And the static picture is m is the maximum of the first I guys.
The point that what I was trying to get to was, how did you know to make that specific statement the loop invariant?
That's a good question. It's a very good question. And when I first started teaching here, my answer was, it's an art form, and it's like painting a Picasso picture. You have to know how to come up with loop invariants. But then, after I was teaching it for a while, I narrowed it down to every loop invariant I've ever seen in this course narrows down to a particular subset of kind of statements, and we'll go through those, right? This is a classic example of more of the input, where you're going through the input at a bit, and you've handled some of it, and you need to handle more of it, right? Any other questions while we're at it? All right, so definition of correctness is, right, we want to say if the precondition is true, and you do anything, and you execute the code, then in the end the postcondition will be true, right? And so in this case, we have an array, we execute the code, we get the maximum. How do you prove this, right? The loop invariant is the picture. I told you already at the top of the loop. Right, so I've had, right, ever since I was an undergrad, I've had people say, well, we don't do loop invariants, we just write code, right? And I just can't conceive of it, right? It's how do you conceive of standing in someone else's shoes and figure out how they think? I mean, I can't conceive of how I could possibly write this code without somewhere in my mind knowing that this was the loop invariant, right? It's just, how did you know to do this without that being in your mind? And if it was in the mind, somewhere in the mind of the coder, then I would claim it was in the mind of the coder before the coder wrote the code. Then why don't you just write it down? You write it down so that the coder can help. It can help the coder formalize, put the pieces together. Right? You can see we have these clear pieces. You got to fit them together, and it helps fit the pieces together. And you write it down. Then the sucker who has to read your code a few years from now, right, will really be helped. All right, and as I say, you don't just add it to make the professor happy, right? I'm claiming this is the way you think about it. This is why when you're standing on the subway, someone says, how do you find the maximum of a first number? You say, well, my loop invariant will be, I have some I and I have some m, and m is going to be the maximum of the first I numbers, right? Yeah?
You know how you were saying in this course is like a subset of loop invariants that like you've done or that like apply to this course?
Yeah.
Do you like make a slide for that?
Dude, what do you think I've been doing for the last 25 years?
Like summarize.
Please wait for it. Wait for it. In fact, I think it's in the set of steps. If you go to that document, they're all written down there. We're going to be going over and over them. This is really the first 20 minutes. All right. Right, use them to think about your algorithm. Right, use them before you start coding. So I like even these steps here. right? We did them in a kind of a funny, order. We did them in order, but I don't like doing them in order. The way I come up with an algorithm is I leap in, from Mars or from wherever, and think, I'm in the middle of this computation. What do I want to be true, right? I kind of, I'm about fairy godmothers. Say, hey, what do I want to be true right now, right? Well, what I want to be true right now is I want to feel like I've made some progress. I want to feel like I have a nice ordered sort of thing happening. So I'm going to say this loop invariant, right? The first thing I'm going to define when I think about an algorithm is what is the loop invariant, right? Yeah?
When you think about the next step, you are not going to think about the whole picture at this moment.
Yeah, this step, I don't like the word step because it feels actiony to me, right? I'm not thinking about code at all right now. I'm leaping into the middle and I'm saying, what do I want to see when I get there? Right? What do I want to see my data structure to look like? And so this is a static picture of what I want my data structure to look like. Right? And then you have to fill in these pieces, and you can fill them in any order. I tend to do this next. Right? How do I maintain the loop invariant while making progress? And that requires me to, it gives me a real good flavor of how this is going. Right? It gives me a sense of what's my measure of progress, gives me a sense of what actions I need to take. And then after I know that, then I can roll back the algorithm backwards and think, how do I establish it? Right? And then I can roll it forward to the end and say, how can I get my postcondition? Right?